So yesterday our goal was to talk about vectors. Vectors are where things have a magnitude and a direction. Really the point of vectors is now to focus on that directional aspect. What happens if something is pointing not directly north or directly south, but what if it's going 33 degrees east of south or something like that, right? You need to be able to handle all those little angles in there. So this really pulls on your ability to do trigonometry. I would say there's four main trig skills I need you to know how to use. The first one is if there is a right angle triangle, do you know the Pythagorean theorem? Can you handle that one? Okay. That being said, there may not always be right angle triangles, but if there is a right angle triangle, do you know how to use that one? Also, if there's right angle triangles, do you know how to use like basic SOHCAHTOA? Sine is opposite over hypotenuse, you know, sort of thing. The new stuff for some of you though is going to be what if there's not a right angle triangle? And we'll do this eventually in class, and I'll give you the Cliff Notes version now. But essentially, the cosine law looks like this: c squared equals a squared plus b squared minus 2ab cosine of capital C. Is that the way they've written it on the formula sheet, by the way, or did they change the lettering around? They wrote it in this format? Okay. So the short version of this is that, there we go, is that really Pythagoras' theorem is the cosine law. Okay. When you guys were taught how to do, you know, a squared plus b squared equals c squared stuff back in grade, I don't know, 8, whatever it is you learned the first time, the truth is you were learning cosine law. It's just you always use something that was a 90-degree triangle. And the cosine of 90 degrees is actually 0. So if all of that's 0, then all of this is basically irrelevant, so we don't bother with it. And it's a good way to kind of introduce kids into doing some of this trigonometry stuff because it makes it simpler. Does that make sense? But the truth is not every triangle is actually a 90-degree one, because clearly looking at this one right here, although I've written the little right angle symbol in the corner, I don't think it's actually 90. So the trick to the cosine law then, if I just rewrite it out here, is that it looks like Pythagoras' theorem. The long side is still C. Actually, it doesn't have to be the long side. What really it has to be is whatever angle you have right here. Let's say this angle is 110 degrees. Then this is capital C across from little c. If this is side little a, we would call the angle across from it capital A. And if this is angle, let's see, here's side B, then this would be capital B across from that. The convention basically is angles are used with capital letters, and sides are used with little letters, and they're always like across from each other. Yours. Okay. So far so good? So really the only change then is you do c squared, you know this number, equals a squared plus b squared, but then you continue with minus 2ab cosine of capital C. So you have to know what this angle is if it's not 90. A similar law, this is actually the one that made SOHCAHTOA. I'll show you a proof later if you want, but it's actually the sine. How did they do in your book? Did they do sine A over A or A over sine A? Okay. Honestly, it doesn't matter which one it is. But it's A over sine A and B and sine B and C and sine C. Darian, you asked me yesterday in math class whether it's possible to have two equal signs. This is actually an example of a formula that has two equal signs, which is kind of strange. So the way it works is that you either need to know about A and B, and you can make this be your formula, or you can know about B's and C's and make that your formula. Or if you'd like to, if the information you have is about the A's and the C's, you can use that as your formula. Let's try another example. Let's do the one we skipped here, just to make sure that you get another chance to see how this works. Here's the picture in the corner. In a lacrosse game, player A passes to player B, then player B passes to player C. Let's figure out the resultant. So, as you can see up in the top corner there, there's already a triangle kind of going here, right, where here's the start going to there to there. The resultant then would be how far it is from A to C. That's what we're kind of looking for, filling the triangle. And just looking at the picture, does it look like it's a 90-degree triangle? No, right? Like, even the angles you're given, there's an angle of 30 degrees somewhere we need to apply. there's an angle of a 155 degree somewhere we need to apply. But I don't think that there's a 90-degree angle in there, right? So this is where we have to use these newer rules, the sine law and the cosine law. They're much more efficient for solving. So, what I'd like to start though is I'm just going to redraw this a little bit bigger than what's happening here. My recommendation, always start by drawing like a grid axis. Just so we know that this is like north, south, east, and west. Start with that. It says that he passed it at an angle of 30 degrees. Well, the way 30 degrees works then is that this is the system where east is known as 0, north is known as 90, west is known as 180, and south is known as 270. So if you pass the ball at 30 degrees would be roughly right about like that. And the 30-degree symbol would be right there. What would this angle right here be then? Yeah, 60. So I mean, if it was useful, I could write that in as a 60. Again, if it's useful. Okay. So that is our first direction, going from A to B right here. Then what I would do is I would redraw a new grid axis. Maybe not necessarily quite as large as the last one, but because then it says that player B passes to player C on an angle of 155. Up here, that angle there is not 155, right? The 155 is the same sort of thing though. This is 0, this is 90, this is 180, this is 270. 155 must be somewhere between the 90 and the 180 spot, right? So 155 must be like about there, right? That makes sense. From here to here is 90. All the way around to there must be 155. So let's see if I can throw some angles in there. If this was at 155, how much further is it from 155 to 180? 25 more. I know it's kind of getting tight for space in here, but that means that right here, that's 25 degrees. That makes sense? And I'll use green. So what we're looking for now is the resultant. How far is it from here to there? So I hope my diagram's a little bit better than the small little one up there in the corner. I'm going to start labeling things now. I'll use a black pen now for labeling. What side am I looking for? The green one, right? It's probably best to call the green one C then. It's typically the way this is going to work here. So that one's going to be C. Which means that over here, this is going to have to be capital C, the big angle right here. Let's pause a bit there. Do I know the entirety of this angle right here? I know part of it. I don't want to say half, but I know part of it is 25 degrees, right? I don't think I can guarantee that the other little half here between the blue and the purple is also 25. But there's some clever ways we can kind of work around this. Let's pretend that I just kept this going over here and this going down here. Wouldn't it meet at a right angle? Because north, south, east, and west meet at right angles. See how this is 30 degrees right here? And that's 90 degrees right here. There's a rule about triangles that says they add up to 180, right? So this angle up here in the corner, I know it's not necessarily the one I want, but this one up here in the corner, wouldn't it have to be 60? But then, wouldn't this be a right angle right here? Meaning that if this is 60, wouldn't the other little bit here have to be 30? Because it would also have to add up to 90? So what's angle C? 55. Okay. The 25 that I was able to write in here, and the 30 I was able to get from there. Those of you guys who did math with me last year, this probably seems a little bit familiar, kind of working with a lot of these little angles in the corners. So So I'll just write down here, angle C, just so I know it's 55 degrees. Okay, I need that. It actually doesn't matter what we choose for A and B to be. Really, it doesn't make a difference. So why don't I make the blue side, let's make the purple one be A, little a, which makes this corner up here big A. And let's let this side right here be little b, which makes this angle in the corner here capital B. Now it's the cosine law. It's essentially Pythagoras' theorem. So it's to find it, it's c squared equals a squared plus b squared minus 2ab, the cosine of capital C. Okay, so what's this little a value? A is whatever the purple line was, right? 12 meters, yeah. We'll skip the meters at this point here. I think units are going to be a bit of a challenge to work with. So we'll just put a unit on when we're done. So we need 12 squared. The b value is whatever the blue line was, which was 9 meters. Normally that's where you stop, right? If it's a right angle triangle, it's just 12 squared and 9 squared, you square everything. But here we got to keep going. We need to subtract 2 times 12 times 9, and then throw in the cosine of the angle. And honestly, that angle is probably the hardest thing to find, because it was like the culmination of like finding small little angles. Here we had a 30, here we had a 155. Neither of those were numbers we actually directly used. Like we had to kind of jury rig it together and piece it together to get that 55 degrees. Well, now it's just a calculator problem. So you take 12 squared and 9 squared, the Pythagoras theorem part of it. But since it wasn't a 90-degree angle, you got to go 2 times 12 times 9 times the cosine of 55. And if your calculator, if you haven't checked recently, make sure that you're in degrees. Because your calculator defaults to radians, for those who remember what radians even are. The answer is not 101 though. Don't forget to square root again. Okay, looks like it's, now I'm going to keep track of that number in my calculator, but at least for writing down my final answer, I get 2 sig digs, right? Because 9 had 2 sig digs. The 30 also would have had 2 sig digs. Right. The 55 that we got from it had 2 sig digs. So looks like green over here is 10 meters. So 10 meters. But that's not it though, right? We also need to have an angle as well. This is what makes this section so challenging. We need to get the angle from the trigonometry too. How'd that first part go though? You guys able to follow? You good? You're shaking your head. Did I lose you?
Yeah.
Where did I lose you?
I'm not good.
On the calculator? Just a quick look. So you will type in 12 squared plus 9 squared minus 2 times 12 times 9 times cosine 55. Is that what you would have done? Okay. Try that one more time just so that it changes. Okay. Anyways, take the 101 then and square root. Anybody else having issues on that, or is that good? Okay. One last thing. We also need to know that angle, because we need to know what angle is coming behind this. It looks to me like the green line is going mostly northeast. But the question is, how northeast is it going? Okay. So we need to now find, really we need to find angle B. That's what we need, right? If we can find angle B right here, that can help us figure out what sort of angle we're looking at. Okay. Let's walk through what we would do if we found angle B. Angle B would be from here to here. But then there'd be a little bit more that would be 30 degrees right here. So let's say we found angle B, and supposedly, let's just pretend, let's say that angle B was 42 degrees. If angle B was 42 degrees, you agree that like from here to the axis would then be 72 degrees? Because 42 and 30 would be 72. So then what I could say is that I'd be going mostly east, but then have to go 72 degrees towards the north. You could say something like that. But the issue is I need to know whether this actually is 42 degrees or not, right? I just made up a number. So to find that angle, it requires a rule called the sine law. So this rule was A over sine A, B over sine B, and C over sine C. Now we don't use all three of them. I just use 2 out of the 3. I don't care which 2 I use. I just need to have the information for them. Yeah, B and C makes the most sense here because we're going to look for this big angle B right here. We have information on C, so we'll just kind of skip doing the A part and just use the B and C information. So now let's plug it in. We know side B, right? Side B was 9 meters. Sine of B, we actually don't know that. We're looking for what angle B happens to be, so I gotta leave that sitting there. C we just looked up, right? We just found C. Now I wrote down 10, but wasn't the answer like 10.01, something like that? Okay, right? So make sure whatever that value is, make sure we use that whole value, go around it. And then we're going to divide by the sine of capital C, which we earlier said was 55 degrees. We'll come back to that in a second. Okay, mathematically, this sine B is on the bottom of a fraction. That's what we're looking for. It cannot be on the bottom of the fraction, so we have to do like a lot of rearranging. We gotta take the sine B and throw it up top over here. If you can envision this without me writing it all out though, now the 10.01 is next to it and the sine 55 is on the bottom down here, so we gotta move this guy back down that way and this one up top that way to kind of isolate for sine B. So bring this one up top there, you've now brought it into the mess, so bring the 10 back down and the 55 up. We need 9 times the sine of 55 divided by that 10 point whatever number it was there. That will be equal to sine of B. Sine B is going to come up top. The 10 number then, we don't want it next to the sine B, bring it down. The sine 55 is also not wanting to be there, we'll bring it up. Now sine B is by itself. So 9 times the sine of 55 needs to divide by that 10 point number, which conveniently I have sitting right there. And I get this 0.733. There's no way that that angle is 0.73 degrees, right? But that's because we're not done. This tells us what sine of B is equal to. So I could say that 0.733 is equal to sine of B. How do you undo a sine? Yeah, that's a good terminology. You need sine inverse to the -1 of both sides. So inverse sine your answer. Inverse sine your answer. Nope. Inverse sine, I gotta type this in now, 0.733188027 What's gonna have to do? 47 degrees. Alright, so I found that angle B is 47 degrees. So let me go back into the diagram, delve back in there. This was actually 47 degrees. So here's how I can respond then. The final answer is it was 10 meters. If this is 47 and we gotta add 30 more, that's 77, right? I could just say 77 degrees then. That's actually valid because starting at 0, working your way around the circle, 77 would work. Or I could say 10 meters and then say something like go mostly east, then go 77 degrees towards the north. That would work. Oh, here's another way that would work. 10 meters. I could say, actually, you know what? I'm not mostly going east. I'm mostly going north. And what I have to do is veer 13 degrees towards the east. Where did I pull the 13 out of? Yeah, 90 minus 77, right? Really, this little sliver right here must be 13 degrees. You could even have written it as 10 meters, 13 degrees east of north. That would work. Really, I don't care which of those methods you pick, as long as you can get the angle. This is what makes physics a little more challenging then, is going forward, not everything is going to be in a nice straight line in linear motion. And this actually applies to most of the units we do. When we do forces in a little while, it's going to have the same issue. When we do momentum in a little while, it has the same issue, because things rarely in real life end up having to go this way and then this way at a nice 90-degree angle. If they always did, that would be lovely, right? But really what's going to happen is, like eventually we'll do forces. Someone's going to push this way, someone's going to push this way, and this might be some sort of resultant, but there's no right angle in there. So there are other ways of solving this. The other way of solving it, if this is really not happening for you, I can show you another method. It's way longer, believe it or not. Like what I just did there is the shortcut. But what you could do is you can make a right angle triangle right about there. You can also make a right angle triangle right about there. And you can find a way to piece it together using multiple right angle triangles. It's a lot more work. But if you can wrap your mind around how these formulas work, you're gonna, I mean, you guys are grade 11. We're learning them at some point. So you just have a head start with something. That make sense? Okay. We'll do more examples in the next couple of days to make sure that you get fluent at this method. Okay, let's move on. Relative motion. There's not nearly as many slides for this one. So this should be a little bit quicker. Let's try a demo. Sorry to you guys on the computer. You probably won't be able to see this all that well. I'm just going to try something. Let's see how this works. Okay. So I'm going to drop this. But I'm also going to be in motion while I drop it. Okay. Where did the pen land? Did the pen land... How do I phrase this? The pen didn't just drop directly down there, right? And what I'm trying to get at here is, as it came with me, here, I'll try to line it up with the chair here. See how the pen landed even with the chair, even as I was moving? Right. Even if I were to be going really fast, the pen is still landing in line with my chair. The reason why that's happening is the pen is also currently in motion. So if I could snapshot what's happening here, as I drop it, it's still traveling forward with me until it falls. Does that make sense? That's the phenomenon we want to talk about today. It's called relative motion, where the pen, from the pen's perspective, like from its perspective, it seems like it's not moving. But from your perspective, the pen is already moving because I am moving. Does that make sense? If I were to be rolling forward, if I were to throw it straight up in the air, it's not going to be behind me when I finish. Okay? If I go forward and I throw it up, why do I catch it? Well, because really what happened is the pen kept moving forward as I was moving forward. Does that actually make sense? So that's what I want to talk about today. It's called relative motion. Sorry, that may not have made sense to you guys. Here's another scenario. Imagine you're on a train. Okay, I like this picture here. No, I want the next slide, actually. Let's do this one here. Imagine you're on a train. From your perspective, you are standing still, right? From your perspective, you are moving no speed, right? But from the guy who's watching you from outside the train, you are moving. Right? And so this is what we need to discuss today. It's called reference frames, frames of reference. It depends on your perspective. If you're this person right here, you think your velocity is nothing. But from this person's perspective right here, if the train is traveling this way, your velocity might be 10 meters per second. If this person in the train right here were to throw an apple up in the air, does the apple like fly backwards and hit the back of the car? The reason why is that the apple itself is still moving forward. Right? If you were in a vehicle and you threw something up in the air, that thing in the air does not just stop there and have the back of the car slam into it, right? Right? That doesn't make intuitive sense when you're moving, right? It's because you and the apple are already moving. This is actually a big reason why we wear seatbelts. From your perspective as a person sitting in a car, your body, right? You are not really physically moving, right? I mean, you know you're moving because you know the car is moving, right? As soon as the car stops, though, what happens to your body? You keep going, right? Because you were still in motion, just like the car. The car stops, you might not. Hence the need for a seatbelt so that you don't go flying through the windshield. Okay? That's the phenomenon I want to talk about today, and how we apply that to physics. So let me go back to the first slide here. Suppose you're riding on a train, it's traveling 40 miles an hour west, but you begin walking towards the back of the train at a speed of 10 miles per hour. How fast are you walking? Well, this really depends on your frame of reference. From your perspective, you're walking 10 miles per hour. But if there was someone able to see you, how fast would the person outside think you were traveling? Anyone want to hazard a guess? 30 going this way. Does that make sense? That would be the right answer. This person here, if they could see you, they would see the train traveling this way at 40. They would see you traveling this way at 10. So that 10 doesn't show up very well. So this person would see you traveling this way at 30. But it depends on your perspective. Do you think you're traveling 30? Well, no, you think you're walking 10. Right? You think you're walking 10 that way, but really because you're inside the train that's going this way, you're actually going this way from the outside perspective. So perspective sometimes really matters when it comes to answering some questions. So same thing with this one here. So the words we're going to use then is called a frame of reference. It's as though it's thought of as any spot you were doing your measurement from. If you're measuring from inside the train, you're walking 10 that way. If you're measuring from outside the train, you're going 30 the other way. If I were to ask you right now, how fast are you moving?
50.
Okay. That was supposed to be hypothetical. How fast are you moving? Maybe you'd say, Chris, I'm not moving, I'm sitting in my desk.
Oh.
Sorry.
Okay.
That's okay. If I asked you, how fast are you moving right now? You'd say, I'm not. I am sitting in my desk and not moving. But I said, but what if the frame of reference was from off of our planet? Our planet is moving at a wicked fast speed, right? But then we could argue that you're actually traveling thousands of kilometers per hour, right? But we don't perceive us to be moving thousands of kilometers per hour, right? We know the Earth is going around the sun, right? But it depends on your frame of reference. So if my frame of reference is the same as yours, I don't currently see you moving. If I could take the planet Earth right here with you on the planet and have me look over here, I would actually see you zipping around like crazy. You get the difference here? That's the frame of reference here.
So,
Yes.
the Earth just stops moving and we all just go flying.
Probably.
What was that?
Right? Because it would be no different than a vehicle coming to a complete stop, right? Right? Our momentum would keep carrying us forward, right? Just like a car would, hence the need for a seatbelt. What was that?
We're not moving that fast, are we?
The Earth is hurtling through space at thousands of kilometers per hour, yeah.
So,
Yeah. Now that being said, why would Earth all of a sudden just stop, right?
I mean, that being said, if the Earth just suddenly stops, like rotation, everything would be obliterated. That's
One of the things we'll mention in the next unit is it's called inertia. Maybe you've heard this word before. The theory is that an object that's in motion will stay in motion, and an object that is stopped will stay stopped, unless something causes it to do that. So the Earth is not just all of a sudden just going to stop all of a sudden. There's no friction in outer space that's going to cause it to all of a sudden like slow down. So I'm not overly concerned about this happening one day. But okay, let's do this example here. So here's where we can apply this sort of scenario here. Let's say you're driving in a boat that can go 1 meter per second across the river, but there's a current that would push you down speed. So let's talk about a couple of words here, some verbiage. What is your apparent speed? What do you think you're traveling while you're in the boat? What does the speedometer on the boat say? It says 1 meter per second. Yeah, if you have that ability, you think you're traveling 1 meter per second. But that's not how fast you're actually traveling relative to someone standing on the shoreline. So if I am sitting in the boat right here, I think I'm going 1 meter per second. But you guys can kind of see by the picture, what's really happening is although I'm trying to go straight across the river, as I get pushed downstream, I actually end up going like along the diagonal. Does that make sense? So I need to find out what the diagonal speed would be. Now the good news for this one here is I've made this a right angle triangle to kind of save us a little bit of time. But you can envision that what we just finished doing might still apply, where what if it's not a right angle triangle? But at least for right now, if this one's going, like we'll make it perpendicular just for the sake of this lesson here. If this is going 1.0 meters per second, and this is going 1.5 meters per second, the actual speed we're traveling, the relative speed, we just need to do Pythagoras' theorem. So c squared equals a squared plus b squared. I mean, if you really want to, you could throw on the minus 2ab cosine of c, but it's cosine of 90 because I'm going to make it a 90 there, which means this whole thing's shot. So what's 1 squared plus 1.5 squared? Square root. 1.8 with 2 sig degrees. So again, this is like the Earth example. We don't think we're moving all that fast. But if we change our frame of reference to being off planet, we're actually traveling quite fast. It's the same sort of thing right here. In the boat, you think you're traveling 1 meter per second, because that's what the speedometer on the boat would read. But the water is pushing you downstream at 1.5 meters per second. So you're actually traveling 1.8 meters per second along a hypotenuse. That makes sense? So this is the actual speed you're traveling. We use the term relative speed. And then let's do one more example here. Let's say the river is 150 meters across. So it's 150 meters from here to here. How long will the journey take? Let's assume we're traveling at constant speed, by the way. The formula for that would be velocity is distance over time, right? Well, I just told you the distance is 150 meters. Which velocity should I use, though? The 1.8, the 1.5, or the 1.0? Actually, the 1.0. Okay, and here's where this gets confusing. You say, Chris, why did we just go through the process of actually calculating the 1.8? Well, the 1.8 is when you're traveling in this direction right here. But if you were traveling straight across, the straight across speed, the y component versus the x component, the y component speed in the same direction as the 150 meters is 1 meter per second. So even though you're actually going to travel more than 150 meters, right, your actual distance traveled is going to be more like 200 meters. I didn't actually calculate it. Right? But in a straight line, from here to here will be 150, even though it's going to go more like this to this to this to this to this. The y component is 150, and the y velocity is 1. Really key point here, then. When you're working with formulas, you have to use x values with other x values, y values with other y values. You can use hypotenuse values with other hypotenuse values, but you can't mix them. Does that make sense? You can't use a y distance with an x velocity. That just does not make sense, right? You can't use a y distance with a hypotenuse velocity. If we happen to know what this hypotenuse was, we could have done that number in the 1.8. So this is the next hard part about physics, is you got to wrap your mind around which values we're using. So this needs to be the 1.0 meters per second. So if you rearrange this, then t is going to be 150 meters divided by 1 meter per second, which means it'll take you 150 seconds. Which we should actually round to 1.5 times 10 to the 2 seconds. Time is actually the link between these sorts of things. Does time have a direction? So in a way, it's going to take you 150 seconds. If there was no current, it would have taken you 150 seconds to go from here to here. But because there's a current, it still takes you 150 seconds to go from here to here. It's just you're getting pushed off course, that's all. So one more time just to make sure that's clear. If we find y components and x components, they have to work with each other in formulas. So what I'm going to start doing in the future is I'm going to start labeling things as dy, velocity initial x, acceleration y, and time. I won't put a letter next to time though, because time is independent of direction. But we're going to have to start indicating what sort of direction these things are going in. I might even go with the distance across a hypotenuse if I want to as well. But I have to make sure I'm clear on those ones. So you actually traveled 1.8 meters per second. But the speed going in the y direction though was only 1 meter per second. And so since the 150 is across the river, that's the value we had to use. It's obviously not a hard question, right? I mean, the math behind this was 2 steps, but the interpretation, that's where you need to have a good reasoning sense, I guess. Okay, different example here. We're not actually going to do math. I just want to talk about a scenario. I encountered this over the summer. Melissa and I went to Halifax. If anyone of you has traveled like a far distance, like across the country and then come back again, one flight is always longer than the other. Here's one. It's Edmonton to Toronto, and I screenshotted this. Edmonton to Toronto is 3 hours 40 minutes. Toronto to Edmonton is 4 hours 6 minutes. Why is there a difference? Is it not the same distance both times? Anybody know why? Not time zones. The wind. Good job. Jet streams.
Michael.
Good job. There's jet streams. And so what ends up happening is if you're flying with a jet stream, the wind is at your back. Although the plane itself, say, is capable of traveling 300 kilometers an hour. I don't know what the number is, right? But if the wind is at your back, you'll actually travel 305 kilometers an hour because it will speed up your relative speed. That makes sense. But if you have to fly into a headwind, your plane is capable of flying 300 kilometers an hour. If you're going into a headwind, you might only be going 295, which slows you down typically. Does that make sense? So that's actually why the differences exist. Right? It just depends on which way the jet streams happen to be either at your back or in your face. So let's talk about another just kind of thought problem here. I didn't actually want to, there's no numbers to solve, I just want to talk about it. So, I've kind of already shown this little one here. Let's say you're in the back of a pickup truck and you throw the ball up in the air. What's going to happen is the ball is actually going to travel with you and you'd be able to catch it again. What's not going to happen is you throw the ball up in the air, the ball will come directly back down. Meanwhile, the truck is over here. Does that make sense? Because what's happening is the ball has a velocity going forward, right? Even though you are holding the ball in the truck, that ball has a forward velocity. That velocity will continue, right? So as it goes up, it will go up, but it'll go forward. It'll go up, it'll go forward. It'll go up, it'll go forward. It'll come back down, still going forward. It's going to come down, still going to go forward. Going to come down. And so therefore, you would catch it again. Right? Just like the scenario where I'm sitting in the chair. Right? If I push myself forward and throw this up in the air, I can catch it, right? It's not like I threw it up in the air and it's behind me. Because I was carrying this forward. It has a speed. Right? So it'll land right in my hand. Okay, so let's try an example based on this with some math now. So you're in your car, you're going 50K. You accidentally drop your iPhone out the window. You stop the car 6 seconds later. Your window's 1.4 meters off the ground. How far back are you going to have to walk to get your cell phone? So just make sure you get the scenario here. I'll pretend that I'm driving the car. And I drop my cell phone. So, cell phone. I'm driving. I drop my cell phone. I realize I dropped my cell phone. Now, the moment I drop my cell phone, don't forget the cell phone is still coming with me as it hits the ground. Does that make sense? So the cell phone did not instantly land on the ground. It actually came forward with me. Does that make sense? So maybe I'll try to draw a picture of this as well. So here's my car. It was going forward. My cell phone, right here, this is my cell phone, just in purple, is also going to be going forward. As it goes forward and it drops, it will eventually land like that. So the moment I dropped it was right here. but it's not going to be right below where I dropped it because it's going to travel forward a little bit and then fall. In the meantime, the car has kept traveling forward. We need to know this distance right there. This is a complex problem, eh? Like, first you just got to wrap your mind around it, and then we got to think, okay, like, well, no. Ultimately, yes, I'm looking for a distance right here. But how am I going to find that distance? I think we need to do two things. What we have to do is calculate, first, the distance the car is going to travel. I got to figure out how far is the car going in 6 seconds. I also need to calculate, I'll use green here, from here to here, the distance my cell phone is going to travel. Because the phone itself is going to go a little ways from the moment I dropped it too, right? If I can find the distance the car went, find the different distance the cell phone went, this will be the, I don't know, let's just write it like this. If I find the, I can't use C both times, can I?
It's like DP for distance.
Yeah, let's go P for phone, that's a good idea. Okay. Okay, so the distance the car goes, minus the distance the phone goes, is the distance I will need to walk backwards to get my phone. Does that make sense? I gotta kind of label this somehow. This is the distance I'm gonna have to walk. It will be equal to the distance the car would have traveled total in 7 seconds, minus the distance the phone would have traveled by the time it hits the ground. That's the distance I have to walk. So far, so good. Okay, let's talk about the car. You're going 50 kilometers an hour, right? So that's my velocity initial. 50 kilometers per hour. Okay, we need to convert that into meters per second. Well, that's not going to work. You guys know how to convert from kilometers per hour to meters per second quickly? Just know how to pull it off? Like I would do meters, there's 1,000 meters in a kilometer. And then there's, what do we need here? 3,600 seconds in an hour. No, I need to cancel that. So 50 times 100 divided by 3,600. What did you get? What's it? 13.8? Okay. What's that the initial velocity of? Well, it's actually the initial velocity of both of these things, right? The car was initially going that speed, right? And so was the cell phone, wasn't it? So both of these things were actually going that speed when we began. So I'm going to say the initial velocity, I'll just write it again here. The initial velocity of the phone was 13.8 repeating meters per second. And the initial velocity of the car was 13.8 meters per second. Both of those items was going the same speed. You can see how physics is all of a sudden kind of ratchet up to a new level of complexity. We don't just have velocities, we have velocity initials of a phone. You're going to hate it even more when I start breaking this up into the x and y direction as well. Yeah, you have to be really good with keeping track of what numbers are which. So. Okay, what about our velocity final?
0.
Yeah, because eventually the car's got to come to a stop, right? So I'm going to make this be of the car though for right now. I'm going to focus on the car for the time being. So the car will eventually come to a stop. We also know the time elapsed because it said the time was 6 seconds. Do I need to put a subscript after time? No, because really the time is pretty irrelevant, right? The time is the same for the car, the same for, well, so I think I have enough information now to find the distance the car traveled. Does that make sense? The formula would be the distance the car traveled would be the velocity initial of the car plus the velocity final of the car divided by 2 all times by time. I'm taking the formula, I'm throwing some more subscripts after it to keep track of the car versus the phone. So 13.8 meters per second, 0, cut it in half, times by 6. How far did the car go before it came to a stop? Got an answer? 13.8 repeating, cut it in half, times by 6.
41.4.
21? 41.4? Okay. That 0.8 number, you guys were using the 0.8 repeating the whole way through?
Oh, I did it.
And Jamie didn't. Okay, so what did you get, Michael?
41.6 repeating.
Okay. So that's how many meters the car traveled. So I'm just going to go back and amend my diagram here. The car traveled 41.6 repeating meters. I'll deal with sig digs when I'm done. Right? But for right now, that's how far I made it in my car before my car came to a stop. Right? I dropped my phone, I instantly hit the brakes. Right? Okay. Now for the phone. Has the phone been falling all 6 seconds? Probably not, right? How long would it take for the phone to fall? Maybe 1, 2 seconds, right? The remaining time, the phone has just been sitting there on the floor. So what I have to figure out is 2 things here. I got to figure out first, how long will it take for the phone to hit the ground? And then once I know how long the phone was in the air for, then I can do the exact same math and try to figure out how far it went. I actually have to figure out, like, this time right here. Maybe I lied a little bit. This is the time that the car was traveling. So I probably should put a C next to it. Because the time that the phone was traveling is going to be less than 6 seconds, right? The phone will have hit the ground after 1 or 2 seconds. So I actually have to break the phone up into, like, its up and down direction. And then its forward direction. I have to break it up into X's and Y's. So again, you can see how this is getting really complicated. You have to have good notation skills. The distance the phone would have fell in the Y direction, I have though, don't I? It tells you how far the phone would have fallen just purely in the up and down direction. It was 1.4 meters, right?
Yes.
In the Y direction, what was its initial velocity? I know it's going forward at 13 repeating, but what was its initial velocity just up and down? 0. Right? As I was walking forward, I know the phone is going forward, but in the Y direction, I dropped it still. Does that make sense? So in the Y direction, technically it was still being dropped. Our initial velocity initial of the phone in the Y direction is actually 0. I dropped it. It does have an initial velocity in the X direction, but not up and down. Does that make sense? What else do I know about the Y direction? Do I know the velocity final in the Y direction? Do I know how fast it's going to hit the ground? It's accelerating though. The acceleration of the phone in the Y direction would be 9.81 meters per second squared. I now have enough information to figure out how long the phone is going to take to hit the ground. I know it's moving forward. Ignore the fact that it's moving forward. That's your reference frame, right? Just think about the phone. If I wasn't moving forward, how long would it take for it to hit the ground? So based on this information, which formula do we need? I think we need this one. D equals VIT plus 1/2 AT squared. That's the one we would use. But I need to make sure I'm clear about this. This is the distance of the phone in the Y direction, the velocity initial of the phone in the Y direction, the acceleration of the phone in the Y direction. Here we go. 1.4 meters. That's how far in the Y direction the phone has to fall. But we're dropping it. So in the Y direction, unless I threw the phone down, or even if I threw it up in the air, right? If I just drop it, it has no initial velocity. So really, this whole thing right here is kind of useless. I don't even need that section there. acceleration. Should I throw a negative on the acceleration? Why not? You're shaking your head. I agree with you, but why not?
It's already going in that direction.
Because the distance was going down, right? And the acceleration is also going down. So if they're going in opposite directions of each other, I throw a negative on it. So this one should just be 9.81 meters per second squared. And then we need the time value. So let's find out how long the phone is going to be in the air for. It's not going to be 6 seconds, right? It will have hit the ground well before the 6 second mark, right? So times by 2, divide by 9.81, and square root. Go.
0.53.
Yes. Cool. I'll just put some dots after it. So, although it takes us 6 seconds to stop the car, the cell phone is on the ground after half a second. Does that make sense? So for our scenario, one more time, I'm walking along with my cell phone. I drop my cell phone, and now I stopped. I originally dropped my cell phone right about here. This is where I originally dropped it, right? In the meantime, I have now kept going 41 meters. Right? But now we need to figure out how far did the cell phone go in that half a second. Okay. Last calculation then. In the x direction. Ooh, I don't want this on. Stop. Uh-oh, did I break my pen? That'd be really bad. Oh, crap. Shit. This is why I shouldn't draw pens. Please work. Shit. This is not good. Oh my goodness. This is turning into a day. Okay. No, let's stuck it on. I don't know what to do. I don't teach in front of the smartboard anymore. I don't even know that it works. Okay. No, as soon as I move this, it starts working. Okay. This may be challenging for the last little bit. Yeah, I broke my pen. Shoot. Okay, we're gonna make this work. First, let's undo all of that. Oh my goodness. Okay. Okay, we're good over here? Yeah. Okay. Don't drop my pen anymore. Okay, I have to try to write this with my mouse now. Okay, in the x direction, we want to figure out the distance that we traveled in the x direction for the phone. That's the last thing we need to figure out. How far did the phone actually travel in the x direction? So that's our question mark. Well, we know the time the phone was in the air for, right? The phone was in the air for this amount of time right here, right? How fast was the phone traveling in the x direction? What was its initial velocity in the x direction? It was what, like 13 meters per second? Is that right? 13.8? Is the phone going to slow down in the x direction? Or speed up? As it's traveling this way right here, what would slow it down or speed it up? Now the car has brakes. So the car slows down due to its brakes, right? In the y direction, gravity pulls it down. But as the phone is moving forward, is there anything actually to get in its way other than air resistance? Really? You know what I'm saying here? So although I had kind of written that it was an initial velocity in the x direction, really that is the only velocity it's going to travel in the x direction. It will always be traveling that same speed in the x direction. In the y direction, it's speeding up. Right? But as it's going forward, it's always going that same speed forward, just like the truck is in. As I throw the ball up in the air, it's always going forward in the same speed. It's the up and down direction that changes. So, this with my mouse. So we're going to say that velocity equals distance over time, because it is traveling the same speed the whole direction in the x direction. So I won't be able to write this nearly as nice as I normally do. You have a time value, right? You have a velocity value. Times that time that you just calculated here by how fast it's traveling, and get me a distance that the phone will be traveling in the x direction. So take 0.54334 and times by that 13.8 repeating number. That should be squared, actually. What'd you get? Say that one more time? 7.4? Okay. Everybody else? I'm assuming there's more digits after that.
Yeah.
Okay. So one more time to write here, we just calculated here. We did three things. We calculated that the car itself was going to need to go 41.6 meters before it finally came to a stop. But it actually is stopping at some point, right? We calculated the phone, it was going to take the phone about a half a second to fall in the up and down direction. So in the up and down direction, it's going to take this long for it to fall. In the meantime, it's been going forward the whole time. So we used that time value and the speed that the phone and the car were originally traveling to calculate the phone needed 8.4 meters, 8.7 meters, whatever.
7.4.
7 point, whatever, that number. I'm so frazzled right now. Stupid board. Anyway, subtract those two numbers. Now you know how far you'd have to walk to get to your food ball. Does that make sense? Okay, minus the fact that I dropped my pen too many times and broke it probably. This is where physics starts to go after a while. You can see this is complex. It's not, I mean, the math is still roughly the same formulas we've always been using, right? But now you have to be able to keep track of, is it for the phone? Is it for the car? Is it in the x direction? Is it in the y direction? We didn't have to use a y direction for the car, right? Because the car was only traveling along the x plane. But the phone itself had a little bit of y component and a little bit of x component. The hint I'm going to give you, time is usually the link. Because the amount of time that something is in the air for vertically is the same amount of time that it's in the air for horizontally. So that's why we had to, I'll use the pen, I can't. That's why we had to first find the distance, but before we went any further, we had to then get a time value to use the time value in the other equation. Another example without my board, two more examples without my board. This is gonna suck. How am I gonna do this? Let me try it one more time. Shoot. No, it's stuck. Shoot. All right. I don't know how I'm going to pull this off now.
You just use a whiteboard marker on whiteboard.
I could, but then they're not going to be able to see it though. See what I mean? That's where my issue is. It's not just for you guys, it's for these guys here.
Did you use like that marker that came with the
They rarely work. Okay, we'll give it a try. I'm just not sure that it's going to actually hook up. Okay, here's what I'm going to try. Sorry, I'm having technical difficulties now. Can you see that? Okay, we'll try this. We'll see how this works. Okay, Next example. Okay, you're in a fighter jet. You're going 25 meters per second in the fighter jet, but you fire the missile at 17 meters per second. You guys get the concept here? The jet itself is already traveling 25 meters per second. You fire a missile. Now, you can't fire the missile at the same speed as your jet, right? Otherwise, the missile will always be right next to your jet. And then, well, that's not good, right? You need the missile to go faster than you're going, right? So, how fast is the missile actually going total, then? I think I heard it. Yeah, right? Because you're traveling 25. The missile itself is traveling 17, right? So now we got to figure out how long it will take to reach the target. So this one's actually a little bit simpler here. The velocity of the jet, sure, it happens to be 25 meters per second. Hope you guys can see that. But the velocity of the missile would be 25 plus 17 meters per second. So what, 42 meters per second. I'm going to be more specific though, that's the initial velocity of the missile. Because it says it's accelerating. So then the missile, the acceleration of the missile is accelerating at 2 meters per second squared. I must have missed a unit there. We have a distance. The distance it needs to travel, I guess the distance the missile needs to travel is 800 meters. Let's find time. This one's actually nowhere near as complicated as the last one, is it? What formula do I use? That'll work. D equals VIT plus 1/2 AT squared. I haven't seen the whiteboard in years. Strange. Okay, so the distance we need to travel is 800 meters. The velocity initial is 42 meters per second. I don't know how long it's going to take. I do know the missile is speeding up more and more though, which is good because it needs to get further and further away from me. Otherwise, when the missile explodes, the plane will be in the blast radius, right? So I need that missile to be going faster and faster away. So 2 meters per second squared and t squared. Is that something you guys can see?
Yeah.
Sorry, it's not as good as normal. What are we going to have to do in order to solve this question? What do we need? Yeah, you recognize this, hey? So let's clean it up a bit. If I swing the 800 to the other side, we're going to have, that becomes the number 1, right? So I'm going to have 1t squared plus 42t minus 800 equals 0. That's the quadratic formula I'm going to need to have to solve. That make sense? 2 times the half is 1. That's your x squared term. 42 is in front of your t term. The 800 came to the other side. Quadratic formula. So negative 42 plus or minus 42 squared minus 4, 1, negative 800 all over 2 times 1. I guess I'll grab my calculator now. First one I got was 14. Anybody else get 14? Okay. With the quadratic formula, you always get 2 answers, right? Yesterday, for you guys in grade 11, we learned a new word. It was the word extraneous. That probably applies to the scenario here. Because the other answer I got was negative 56. Anybody else get negative 56? Okay, you can't have negative time. You didn't get 56?
I would need 100.
Did you divide by 2? No, I have to do the whole divide by 2, eh? Okay. So, I would say this is a good example of an extraneous solution. It's where, did we do our math wrong? No, we totally didn't mess up anywhere. But since this is referring to time, you can't have negative 56 seconds, right? Like, that's just not logical. So I would say that, we just need to omit that one. So it's going to take 14 seconds for it to reach target. Sound good? Alright, last one. I have to erase this. Oh my goodness. Okay, so I've learned, don't drop really important things when talking about physics lessons. Okay, plane is traveling 350 kilometers due west in 2.25 hours, but there's wind. Kind of like the example we talked about with Edmonton to Toronto, the wind is going to push you a little bit off course, isn't it? So the question is, what does the plane's air velocity need to be in order to reach the airstrip on time? So let's draw a bit of a picture here. Here it needs to go due west. So here's the plane, and it needs to go directly west. That's what it has to do. It needs to go that west amount in 350 kilometers. And, well, let's convert that even. That is 350,000 meters. That's how far it's got to travel. And it's got to do that in 2.25 hours. So that's its like distance in the, let's call it the x direction. Is that amount there? And the time it has is 2.25 hours, which is 8,100 seconds. So far, so good. That's what it needs to accomplish. Here's the problem. There's wind. And the wind is blowing north of west. I really wish I had put this a little further down on the page. The wind is going north of west, right? So that means the wind is going this way. Does that make sense? It's going north of west. And the 65 degrees is right here. That's where the wind is going. This black line right here, that's our resultant. I've actually given you the resultant. Does that make sense? This in red is the air. What we need to calculate, I don't have the color, so I do this green over here. What we need to calculate now is, what does the plane actually have to travel? This green right here would be the plane's velocity. This is its plane's velocity. Does that make sense? The plane is actually going to have to head a little bit kind of south in a way, because it needs to compensate for the fact that the wind is going to push it this way. Does that make sense? Now, it's not actually going to occur in this order, but I mean, you can think of it like this. First, the plane gets up into the air and just lets the air push it off course for a little while. Okay? And then we turn off the wind and let the plane keep going this way instead. But that's not actually how it works, right? You don't just like let, you know what I'm saying now? Okay. So simultaneously, this is what's actually going to occur is the black line here. So what we need to do is figure out the green line right here. So this is kind of where we started class in a way, isn't it? Right? With our cosine law, sine law stuff. So let's fill in what I know though. This right here was 40 kilometers an hour along this little bit right here. So can we convert 40 kilometers an hour into meters per second? I get 11.1 repeating meters per second. That's how fast the wind is pushing us with this angle right here. We also are going to need to know this one right here. Now, if I'm working in meters per second, can I calculate how fast the plane is going to actually need to travel along its trajectory? Could we pull that up? Just take these two numbers and divide by each other, right? So if I took, to find this velocity in the x direction, it would be 350,000 meters. You got to travel that distance in 8,100 seconds. 43.2. Oh, sorry guys, we just run out of time here. I'll try to finish this in a little while. I wish the recording would show though. What did you say it was?
43.
So here's what we've got. We've got one side here at 43.2. We've got another side over here at 11.1. Here's the good news though. I have an angle. I know it's not 90 degrees, but I have an angle. So we're using cosine law, right? Let's make this be C. It makes this guy over here capital C. We'll make this one here be A. Makes this angle here capital A. We'll make this side here be B. Makes that angle capital B. So what am I looking for? Yeah, I need to know how fast does the plane have to think it's traveling? Okay. That's not what the plane is actually traveling, but the green line right here is what the plane thinks it's traveling. Right? The black line is what it's going to actually do. The red line is how the wind is going to push it, and it needs to compensate by going this way. So, c squared equals a squared plus b squared minus 2ab cosine of c. But I know most of these numbers, don't I? A is the 11.1 number we just calculated. B is what we actually want to travel, the 43.2 number. Repeat it. And then we need the cosine of C. But I have that, right? Because it said we were going 65 degrees north of west. 65. You're at 39.8. Okay. Shoot, we only get 2 sig digs though. The degree sign we used right here, that does count. So 39.8 means I guess we should make it 40 meters per second. So you're the pilot sitting in the plane. How fast does the plane's readings have to say? The plane's readings have to say that you're going 40 meters per second. Okay. You're actually going a different speed. You're not going 40 meters per second. You're actually going to be going 43 meters per second. Okay. Why are you going actually 43 meters per second? Well, the wind is kind of at your back. Does that make sense? So the plane itself only has to travel 40 because with the wind at your back, you're actually going to travel 43. The other problem though is you have to aim the nose of the plane a little different. The wind is going to push you up. So you're actually going to have to aim down a little ways as well. I think just due to time constraints, we'll probably end it right there. But we may actually at some point be asked to calculate what direction you're traveling the plane. If you had to do that, what you'd do is you'd find this angle B right here, and then you'd do a little bit of work with the symbol right there. What you'd do is you would know that this guy right here is 65, which makes this 90, which makes this 25. That makes sense. So this would be 65. This would be 90. It would make that little bit right there 25. If you could find all of angle B, you could then find this portion right here, and that's how far west of self you'd have to travel. I'm running out of time. That makes sense. Okay. Wait, tomorrow's a work day. We need some time to practice into these things here. So I will see if I can figure out a way to make my board work better too.